Hello, everyone. We're still waiting for some people to join the meeting. So in the meanwhile, why don't you all type in the chat what you did for July 4th? If you did any fun, did you watch fireworks? Did you have some good food? Like, did you watch a movie or something? So type in the chat what you did for July 4th while we're waiting. Okay, some people watch some Netflix, some fireworks, sleeping, nothing. Oh, a sleepover. Sounds like a lot of fun stuff. Okay, we will wait just like one more minute and then we'll get started. Thank you all for your patience. Oh, wow. Okay, so Alan ate a cheeseburger, 2 hot dogs, and 2 slices of pizza. That's a lot. Okay. And just a reminder, make sure to turn on your video camera, your web camera, so that I can see your face and make sure you're not sleeping or, playing video games or something. And then also, we will be recording this lesson to put on the YouTube channel for you to watch later. But in that recording, none of your faces will be in it. So just make sure you're muted during the entire meeting. Okay, I think we're good to get set started. So, okay, so we're gonna get started now. So welcome to SALY again. And this lesson this week is a little special because we have a guest presenter, which is my brother, Sean. And he wanted to call this his tree special edition. So, Sean, why don't you get into it?
All right. Hi, everybody. So I'm Sean, William's brother, and today we are going to be talking about, actually, well, before we do that, more about me. I'm Sean. I like a lot of outdoor stuff, so fishing, archery, camping, hiking, wood carving. Like my brother, I like cheese, but like he always says that mozzarella cheese sticks is the only way to go. I don't believe that. I think all cheese is good. And then I study chemical engineering and computer science at UC Berkeley. So today we are going to be talking about chemistry, and one sec. Let's see. Okay, so today we're going to be talking about chemistry, and I know a lot of you guys are kind of young and you might think that this is a really difficult topic. And while it can be a very difficult topic, I think the very fundamentals and basics of chemistry are pretty accessible to almost anybody at any age. So what I want to talk about is how chemistry is built on the fundamental, like very basic ideas. If you can understand like these basic ideas, then eventually as you grow older and you start taking classes in middle school and high school, you'll start to learn more about the specifics, and then you can start applying it to cool things like, solar panels. You can apply it to like computer chips, even, chicken nuggets. All those things like require chemistry. Even things like clothes that you wear, like the materials that are made from it, are all because of chemistry. So could you guys type in the chat, like what are some other examples of like things that use chemistry that you guys know about? I see Sean's dad is a chemist. That's pretty cool. Cakes would also, be a good example of chemistry. Cooking and baking actually involves a lot of chemical reactions to make, stuff taste good. Yes, chemistry. That is what we are doing today. Soaps and detergents. Yep. The reason why soaps and detergents work, a large part of it has to do with chemistry. These are very good ideas. Even milk. Milk in itself is really interesting because, you know, the way they preserve milk and make it safe for us to drink, you know, pasteurizing is actually a chemical reaction as well. Yep, all these ideas are very good. Soda is good chemistry, is talking about the dissolving of gas and liquids. Even pencils. Pencils can also be chemistry. All right, these are good examples, but I think we're going to continue on. So what is chemistry? I would like to say that chemistry is the study of atoms and their structures to find out what properties they have and how they react with each other to make things. So we're going to be talking about these concepts and these like different parts like atoms and structures and properties a little bit more in depth. But first, do you guys have any idea what atoms are or any reactions? Because I know there's a large age range here, so I want to get a little bit of a feel of what you guys already know. So do you guys know anything about atoms? And if so, like, you know, you can type what you know in the chat or anything about reactions. All right. Well, it seems like some people say they know a little bit. Tiny little things. Yeah, atoms are very tiny little things. So I think we're going to keep talking about atoms then. So atoms, the reason why people started studying atoms and how they discovered it was there's back in a long time ago, there were these philosophers slash scientists, and they thought to themselves, like, if we had like a piece of gold or a piece of silver and we cut it in half, it's still gold or silver, right? So they were just wondering, like, if you just kept cutting in a half and a half and a half, at what point would it stop being gold? So what they were trying to do is they're trying to think like, what's the smallest part I can divide something into where it still acts the same as like the bigger pieces? So what they ended up discovering through a lot of different kinds of experiments is that there are these things called atoms. This is the very, very, very smallest thing that you can have that acts the same as like the bigger things that it can build up. So atoms, as you can see, are made of three parts. They're made of neutrons, protons, and electrons. So with these tiny little particles that make up the atom, they all have their own charge. It's kind of like an electrical charge or like kind of like a magnetic charge. So I don't know if you guys have played with magnets before or anything like that, but for magnets, there's like a positive and negative side. And then because of that, they attract. So for these neutrons, protons, and electrons, neutrons are neutral. That means they don't really have a charge. So they're not really affected by protons or electrons in terms of attractive by charge. So protons are positive, and you know, as like kind of like the pro in front of or like the P in proton stands for like positive, and electrons are like negative and small. And electrons are actually called electrons, and the reason why electricity is you know, they all have the same like ELECT in the beginning is because they're very much related. I don't think we're going to go in too much into detail today, but that's just something to think about. And one thing we're going to continue to talk about in a little bit is how different number of protons, so each atom, the number of protons they have determines what element they actually are. And yeah, if you put in two negatives, like Evan said in the chat, they kind of repel each other. Okay. So one thing that I wanted to mention is like, if you look at this picture here of the atom and you look at our solar system picture, they're very similar. So they're both held together by these forces. If you can see here, they both have like these rings and these things orbiting around the center. So can you guys type in the chat, like, do you guys know any different kinds of forces? Any examples? Yep, gravity is one. That's a good one. Gravity is what allows, you know, the planets to stay in orbit around the sun. Yeah, so a lot of people are putting gravity. That's good. Okay. So one thing is, oh, whoops, did not mean to. One thing is that these electrons are on the outside. So they're orbiting something called the nucleus. The nucleus is called the nucleus because it's the very center of the atom. So the nucleus is made of protons and neutrons. Compared to electrons, the nucleus is like very like big. It's has a lot of mass. You guys know what mass is? You guys can type in the chat if you guys have Okay, so some people are saying weight. So mass is a little bit different than weight. We won't go into too much detail about the difference between mass and weight, but the basic idea about mass is just how much stuff there is, how much physical like things are built into the object. So the nucleus, unlike this picture, is actually very, very big compared to electrons. Electrons are very, very tiny. They were saying that if the nucleus was like an entire football stadium, like the electron would be just like a single grain of rice inside the football stadium. That's the difference between the size of the center of the atom and the little things floating around it. Kind of like how our sun is very, very big compared to the planets, right? You can fit thousands and thousands and thousands of Earths inside the sun. So a little bit about the periodic table. This periodic table, we're not going to go into too many of the complicated, symbols and numbers, but the periodic table is one of chemistry's like biggest tools. Something that's very basic to read a periodic table is you have these symbols. These symbols each represent an element. And like I said before, an element is different. It's all the types of atoms that have the same number of protons. That's what determines what element an atom is. So if you look at this number on the very corner of each square, this number actually tells you the number of protons in that element. So if you look at this is H. H, you don't have to know this, but H stands for hydrogen. And then this one in the top just means that hydrogen has one proton. And then that means any atom that has one proton is hydrogen. And yeah, Zoe said that weight is a value calculated by gravity, mass, and density. Yeah, weight is technically a measure of how much gravity pulls on mass, but we'll save that for a different lesson. Okay, so we're going to continue talking about forces here. So forces can attract things together or repel them apart. So I think you guys might have mentioned this a little bit, but what kind of force do you think keeps the planets going around the sun? Some people are saying gravity, some people are saying magnetism. Okay, so for things about the planets going around the sun, most of it is gravity. As for magnetism, within each planet itself, the planets might have a magnetic field, but compared to the gravitational pull between the planets and the sun, it's very, very small, if not none. Gravity is correct, yeah. So why do you think electrons are attracted to protons? What do you guys think keeps the, electrons circling the nucleus, which is made of protons and neutrons? Do you guys have any guesses? We talked a little bit about the charges between, what Alan says, magnetism and attraction to each other. Yeah, it's kind of like a form of magnetism. So in the center, you have these protons and neutrons, right? And then they kind of form the core. And then overall, that would be like a positive charge. And then the electrons going around and orbiting have a negative charge. So just like magnets are attracted to each other, the electrons are attracted to the protons. And that's why they continue to circle around in orbit. So I'm going to teach you guys a little bit how to calculate the charge of atoms, because not only do electrons and protons and neutrons sort of have a charge, but atoms, they can be charged too. So when you look at an atom, you only have to count its protons and electrons to figure out its charge. Can anybody guess why you don't have to include neutrons when you calculate its charge? Yeah, exactly. Neutrons, they don't have any charge, so they don't really affect the overall charge of any atoms. So let's look at this. Let's say you have sodium. Now, sodium has 11 protons and 11 electrons. So because they kind of cancel each other out, sodium has 0 overall charge. But what if one of those electrons kind of flew away, it left? Then you only have 11 protons and 10 electrons. So then because you have more protons than electrons, you're going to have a positive charge. Now in chemistry, we like to simplify things a little bit. We say that protons have a charge of +1 and electrons have a charge of -1. So that's why when you have sodium and you have 10 protons and 10 electrons, that's kind of like +11 -10. So that's why you have an overall charge of +1. Now if we look at chloride here, chloride has 17 protons and 17 electrons. So in that case, it's going to have, again, a 0 overall charge. However, if you add in a charge, you're going to have 1 extra electron. So if you have more electrons than protons, you're going to have a larger negative charge. And then overall, this atom is going to be a -1 overall charge. So if I were to ask you guys, if a atom had 5 protons and 7 electrons, what would be the charge of that atom? Yeah, some people are saying -2. So yeah, you would get -2 because 5 minus 7 is equal to -2. So this is how atoms become, positively and negatively charged. So when these atoms become positive and negatively charged, just like electrons were, attracted to the protons within the atom itself, when an atom becomes either positive or negative, they can attract each other too. So if you had, for example, in our previous example, we had sodium that lost an electron and became positive, and then we had chloride, which gained an electron and became negative. So in this picture, we have our negative chlorides and our positive sodiums. And because of their charges, they attract each other. And then this is how we have different compounds and molecules form. For example, I don't know if you guys have heard this, but NaCl is like salt. So like the table salt that, put on food and that sort of thing, that's NaCl. And that molecule is formed because of the different charges of the atoms. Now, another thing, and might be a little bit more of a difficult topic, but if you think about when you put like salt in water, it kind of disappears. So a lot of people, they don't understand, where does it go? Does it just become smaller, or like what happens to it? So water itself, do you guys know the formula for water? Yeah, a lot of people are saying H2O. That's exactly right. And one thing about H2O, the reason why it's called H2O is because it has 2 H's and 1 O. So like we said before, H is actually hydrogen and then O is oxygen. So when you look at a water molecule, this big red thing right here is going to be the oxygen, and these 2 white things, they're like hydrogens, okay? So because of the way and the sizes, we're not going to go into too many details, but the water ends up having the oxygen atom becoming more negative and the 2 hydrogen atoms becoming more positive, okay? So because of this, you can imagine kind of like a magnet that's kind of weird. It has like 3 sides where the top of it is positive and the bottom part is negative, right? So just like sodium and just like chloride, water can also be charged. In this case, the top of water is negative and then the bottom of water is positive. So when you add in these NaCl molecules, we already know that sodium and chloride, sodium again is positive and chloride is negative. So what do you think the sodium molecule is going to be attracted to, the top or the bottom of the water molecule? So if sodium is positive, do you think it's going to attract to the top or the bottom of the water molecule? The top of the water molecule is going to be negative, and the bottom of the water molecule is positive. Yeah, so like I was seeing in the chat, sodium, because it's positive, is going to be attracted to the top of the water molecule because that part's negative. So just like we were talking about before with magnets and electrons and protons, the sodium is going to be attracted to the top. So then where do you think the chloride is going to be attracted to? Yeah, people are saying the bottom, and that's absolutely correct because the chloride is going to have a negative charge, and then because the water molecule, the bottom is positive, it's going to attract there. So actually, this is strong enough in water where the sodium and the chloride, instead of being attracted to each other, when they enter in the water, they're surrounded by all these different, positive and negative charged, water molecules. So then this actually forces the NaCl, the sodium and the chloride ions to like break apart. And then, so the water molecules themselves will surround these different sodium and chloride. So that it actually pulls apart the molecules. And then that's why it dissolves. It kind of like disappears. It's all because of the different charges of the different atoms and how that interacts with each other. That might sound like kind of like a complicated thing, but in the very fundamental, the very basic thing, it's just because of like kind of like magnets, positive and negative attract. And then that's what causes a lot of these bonding. And that's also what causes a lot of this dissolving. Does anybody have any questions about what we've gone over so far, either with atoms themselves or anything about, the different charges or how they attract to each other? Feel free to message me or my brother in the chat. And anybody, okay, so does it seem like anybody has any questions? Just to make sure, if you guys feel like that you're understanding this, can you give me either a reaction or a message? Nice, I see thumbs up from Alan. See thumbs up from other people. Nice. All right, cool. I'm glad you guys are sticking with it. So this is going to be, again, another harder topic, but I think you guys are very smart people and will be able to understand this. So when I talk about reactions, I talk about different atoms coming together to make something new. So just kind of like, if you're at like the soda machine and like a buffet or something like that, I don't know if you guys have ever tried this, but like, mixing different like drinks together to try to make like a new drink. Like it's kind of like a similar idea. What we're doing is we're taking individual ingredients and then we're mixing them together, and then something happens to create something new. It's kind of like baking too, where you have like individual ingredients to bake a cake. So like a cake isn't just like, you don't just put in like egg and flour and all that stuff like in one place and then magically becomes a cake. No, you actually have to like cook it. You have to like bake it. You got to stir it around and that sort of thing. So chemistry and the reactions, these, you don't just put the molecules together, but a lot of things happen on a very, very tiny scale that you can't really see, that causes reactions to happen and new molecules and different things to form. So I guess I've been talking about molecules a lot, and I guess I never really said what a molecule is. The difference between a molecule and an atom is just one tiny thing. It's just like one little particle, and it's of one particular element. Now, a molecule, on the other hand, is when these different atoms come together to form like bigger things. Like, we said water is H2O. That's two H's and one O, so that's two hydrogens and one oxygen. That would be considered a molecule because it's more than just one atom. Now, you can also have molecules where you have more than one atom of the same element. So for example, oxygen, even though it's an element, it also could be a molecule because you can have two oxygen molecules come together and bond together. So even if two oxygen molecules are joined together, that would also be considered a molecule. So to talk more about reaction and bonding, a lot about chemistry is answered by the question of stability and energy. So let's go over what stability is. Stability is kind of like balance. It's very comfortable. I don't know if you guys like, in the winter when it's like really cold outside and you just want to stay underneath your warm blankets, it's like a place you want to be. It's very like, comfortable. It takes a lot of energy. I don't know about you guys, but like when I'm like in under some like warm blankets in like a really cold winter, it like takes a lot of energy for me to get out of bed and to start like moving around and that sort of thing. That's kind of what like stability is. It's it's being in a place where it's comfortable. In the case of chemistry, it's being in a place where like the atoms are comfortable. So stability also shows like what's likely to happen. You guys being in elementary school, I don't know if you guys like do a lot of like flipping the water bottles and that sort of thing, but so if I were to ask you guys like what's more likely, are you guys more likely to flip a water bottle and it lands like cap side up, or is it more likely for you to flip a water bottle and like mess up? Yep. So when you flip a water bottle, it's a lot less likely for it to land on its cap. It's a lot more likely for it just to fall over or just like fall everywhere, right? So what do you think is more stable? Do you think it's more stable for a water bottle to be flipped on its cap, or more stable for a water bottle to flip and just like land on its side? Yeah. So in this case, it's actually a lot more stable for a water bottle to land on its side than on its like cap. And then that also shows you, that stability also like things tend to go to where things are more stable. So another thing about stability and energy, when you wind up a toy, like those wind up toys where you have to turn the thing, if you wind up a toy, you're giving it energy. And when you give it energy, it's able to like move around and jump and flip. Do you guys think that when you give it energy, it's could be making it stable or not stable? Yeah, that's correct. A lot of people are saying that it's unstable. The more energy you give a toy, the more the more energy you give the toy, the more it moves around. That's kind of like it's kind of like crazy, you know? So another way to think about like whether something's stable or not, if it's acting crazy, it's probably not stable. What it wants to do is eventually that energy runs out and it stops moving, right? So when it runs out of energy and it stops moving, the toy becomes stable. It's out of energy. It's at lower energy. So what we can learn from this is that the lower the energy something is, whether it's a toy, whether it's an atom, when it's at a lower energy, it's just more stable. So here's another example I wanted to talk about. If you put a ball at the top of a hill, do you have to like push it very much to make it roll? Yeah, people are saying no. When you have a ball at the top of a hill, you don't have to push it too much to make it roll. This is so do you think and then if you have a ball and it's at like a valley, so like you see on the picture on the right, if you have a ball in the valley, does it take a little bit of energy or a lot of energy to push it up the hill, to make it roll up the hill? Yeah, people are saying a lot of energy. So if you have a ball at the bottom of the hill versus the ball at the top of the hill, what do you guys think is more stable? Do you think it's more stable for the ball to be at the top of the hill, or do you think it's more stable for the ball to be at the bottom of the hill? Yeah, it's more stable to be okay, so Alan said because less gravitational pull and less energy. That's not entirely true. The gravity pull is the same, but the difference is that it's in a position where the gravity can affect it more. It's in a position where a little bit of energy can move it around a lot at the top of the hill. And that's kind of like what the idea of stability is. If you're in an unstable spot, you're in a position where a little bit of energy can make you, change your position. And then if you're in a stable position, it takes a lot of energy to leave it. like we were saying before, chemistry is all about these atoms trying to be in the most stable place. So it's more likely for an atom to exist in a stable position, because if it's not in a stable position, like if it's at the top of a hill, it's going to eventually go down into like the bottom of the valley. Here's another question for you guys. If I had, let's say, 100 hills, and I put a ball at the top of the, actually, let's say I have 100 hills, and I put a ball at the top of each one of the hills, or let's say 50 of the hills, and the other 50 of the hills, I'll put a ball in the valley of the, between the mountains, right? If I waited, let's say I put a soccer ball at the top of each hill. Let's say I waited like a year and I came back. Do you guys think more balls would be in the valley of the hill, or do you think more balls would be at the top of the hill? Yeah, people are saying that, some people are saying valley, some people are saying top. Okay, so if I had, let's say we said 100 hills and 50 of the soccer balls are on the top of the hill and 50 of the soccer balls at the valley of the hill. If we left it for a year, there might be a lot of things that happen. There might be wind that blows it around. There might be, I don't know, there might be earthquakes or, animals that move it around. So let's say we had like a lot of wind that year. That means at the top of the hill, these balls, they get a little bit of wind and then they'll just roll down. But once they're in the valley, do you think there's going to be enough wind to push an entire soccer ball up a hill? Probably not. Yeah, people are saying no. And that's kind of the idea of stability. Over time, more things are going to want to be stable because of probability and luck and chance, because it's just more likely for things to move from an unstable position to a stable position. And going through middle school, high school, and even college chemistry, that's one of the biggest ideas that you guys will learn. And you just learn different ways to measure stability, I guess, is how you guys will continue to learn. So again, reactions take place to make things more stable and lower in energy. To talk about it again, reactions are different combinations of energy and atoms to make new compounds. No, unless there's a tornado. Yeah. So here's a chemical reaction. Again, we're looking at water. So we said that water is 2 hydrogens and 1 oxygen molecule, as you can see from this. So in a chemical reaction, the very, very basics is that you have something called reactants. And one way you can remember that is that reaction, reactant. So you put in reactants, they're kind of like your ingredients, like when you cook, like they're the things that are going to react. So these reactants, they come together and they create products. Products would be like the end result. That'd be like the finished product. That'd be like the cake you have at the end. So, oh, I see some people are trying to annotate. Can we try not to annotate? Let's see. Cool. So then one thing I want to ask you guys before we go to the next slide, or if you guys have any questions about reactions, feel free to text me or my brother. And then my question for you guys is, what is mass and energy? We talked a little bit about mass before, so you guys don't have to answer that one. But what do you guys think energy is? Do you guys know of any different kinds of energy? Actually, it's okay to text the entire chat this answer too, because hopefully there are lots of different kinds and people can see each other's kinds. So heat, push, and pull is energy, basically stability. Energy cannot be distorted, created. Electrical, wind, heat, thermal, electrical. Okay, so heat is definitely a kind of energy. Push and pull is not necessarily energy, but it can be a kind of force, like we were talking about earlier. The difference between energy and a force is energy, it has to like be able to like change forms like between each other. Like heat can become, electrical, can become thermal, can become wind. Or wind is not a type of energy, but wind can help generate electrical energy. Yeah, that's correct. Hydropower can generate can generate energy, but hydropower actually uses the energy of gravity because the gravity pushes the water down, and then the water will turn a thing. So let's go to our next slide then. Oh, oops. Is it on that? Okay. So reactions, like many things in science, are controlled by laws of nature. Today we're going to talk about one of the different kinds of laws that chemistry has to obey and has to follow. Like someone mentioned before, there's the law of conservation of mass and energy. So mass and energy can never be destroyed. They just move around and become different forms. So an example of this is atoms can rearrange. Heat can become light, and sound are trapped in atoms. So let's see, what else is, okay, let's talk about this a little bit more. So when I ask you guys, if you have like a fire, like let's say you burn some wood and stuff like that, at the end you're left with a bunch of ashes. So doesn't that seem like it kind of like breaks the rule of mass and energy? Where did the mass and energy go after you like burn a log of wood in like a fire? Some people said chemical energy, heat energy. What about like the mass? Like where did the mass of the log go? Because at the end you're just full of like just ashes, right? Like it seemed like the giant log could become like just a tiny bit of ashes. Okay, so in this case, maybe let's start with a different example. So let's say you had a reaction where you have like water and actually, let's say you were cooking like a cake or something like that. When you have the ingredients and you mix them together, like the ingredients are still inside the cake, right? They don't like leave, right? That'd be an example of conservation of mass. Um, so when we talk about like fire and we talk about burning a log, the log has mass. And when you burn the log, that mass doesn't just disappear, it has to go somewhere else. So where do you think the mass is going? Is there anything leaving a fire? Yeah, Evan said smoke, and smoke is definitely one of the things. So when you burn a fire, you have smoke that leaves. So the mass that was in the log is becoming a new form. It's becoming the smoke that's leaving. And then before someone mentioned chemical energy, and that's also correct. Energy, remember, cannot just come out of nowhere. You can't just have like, fires give off a lot of heat, which we said before is a kind of energy. That energy just can't come from nowhere. It's not like magic. So we're not going to go too much into detail about this, but different chemicals and different atoms and molecules, they contain energy within themselves. And then this energy can be released when these different atoms and molecules are like broken apart or they come together. This releases energy. So this chemical energy can become something like thermal energy. And another thing about, I guess, some more examples of energy becoming different things. Let's see. Like for example, when you heat a pot of water, like when you have a fire underneath the pot, that fire has a lot of heat energy. So where's that heat energy going to? Guys, let's also try not to spam the chat too much so other people can see the answers. So to reiterate, to talk about my question again, when you have like when you're boiling some water and you have the fire underneath, where's the energy from the fire going into? Yeah. The energy is going into, actually the answers, all these answers are correct. It does go into the boiling water, but some of that heat, like, goes above the heat, above the heating kettle. Like if you ever felt the air on top of like a boiling thing, that's hot too. So the heat's going there, it's going into the vent. It's actually, dissipating, or is going all around. It's going into the air, going into the environment. So this different, that's just one kind of like energy being transferred into a new location, right? It starts as a fire, but then it turns into like heat in the air. And another thing that people like, I don't know if you guys have learned about factories or that sort of thing. When they have, burn coal to create electricity, they burn and then they create steam from the water, just like when you boil water. And the steam turns like these giant generators that creates electricity. So that's an example of the heat from the fire becoming a different kind of electricity, energy, which we said is electricity. Let's see here. Does anybody have any questions about the law of conservation of mass and energy? Actually, here, to go back to this picture, we talked about law of conservation of mass and energy and different things like fires and like other examples. But here's what it'd be like. You don't have to understand this picture because it's a little bit more complicated, but just to give you guys an idea of what you might see in the future is you have methane, which is just a kind of gas, something that you might have like, in your stoves or something that like when you light will, catch on fire. You can use it to like cook stuff. And then you have oxygen, and then you have carbon dioxide, and you have water. So you don't really need to, the names of the things aren't really that important in this case, but what you can see is you can see like CHOs on both sides, right? Can you guys tell me how many C's you see on the reactant side of the reaction? Yeah. There's one C on the reactant side. What about the products? How many C's do you guys see in these? Yeah, exactly. So then what about H's? How many H's do you see on this side? I guess one thing to notice is that if it's a little bit like, if it's a little number like right here, this means that there are 4 H's. So I guess that kind of gives away the answer, but I never really spoke about that too much. And if it's like a 2 on the outside, it means it's 2 times however many is inside here. So for oxygen, it'd be 2 times 2, which is 4. Okay, so I will go over this because I guess it's a little bit complicated. But on the product side for H2O, H2O already has 2 hydrogens, right? And if you have 2 H2O, that means you have 4 hydrogens. So just like on the left-hand side, the left and the right-hand side both have 4 hydrogens. And the left and right-hand side both have 1 carbon. And then here, we look at oxygen, oxygen has 2 oxygens for each one, and it says we have 2 of 2. So that means we have 4 oxygens in total. And because we have 4 oxygens in total on the left-hand side, because of the law of conservation of mass and energy, we have to have 4 oxygens on the right-hand side too. And that could be shown by, carbon dioxide has 2 oxygens. And then water, we said, water has 1 oxygen for every water. And if there are 2 waters, then, we have 2 oxygens. So 2 plus 2 is 4. So if you look here, both the left-hand side and the right-hand side have the same number of atoms on each side. This shows us that these atoms, they don't like disappear during reactions. They just become different things. Like before, C was in something called methane, and when it reacts, C is still existent, but now it's just rearranged into something new, which is called carbon dioxide. So this is an example of doing a reaction using the rule of conservation of mass and energy. Now, I just want to say that, here, actually, we'll go to the next slide first. So today, let's try not to annotate, okay, guys? Let's see. So what did we learn? Today we learned that chemistry is about studying the structure of atoms to understand their properties and how they will behave. So today we learned that atoms are made of like three parts, electrons, neutrons, and protons, and the number of protons affects which element it is, and that these are all held together by forces, making them look kind of like solar systems, with protons and neutrons in the center, and the electrons kind of orbiting the outside like little planets. So we also learned that the main idea of chemistry and reactions is that atoms react to become more stable and lower energy, like we talked about with the ball and the hill. When atoms want to get into that valley, they want to get into a very stable, very comfortable spot, and that's why they react. And then also we learned that in reactions, the conservation of mass and energy must be followed. I just want to say that today this lesson is not to make you guys, chemistry like, geniuses. This is just to show you guys the very, very fundamentals and basics of chemistry. And that hopefully like you'll take these ideas of like stability and energy when you guys learn more about it in like middle school and high school. And chemistry really is a very useful field. It makes a lot of things that you guys use every single day, like from anything from your clothes to your food to the energy that like allows you guys, to charge like, your phones or like your house, your lights. It all has to do with chemistry. So it's definitely a very interesting thing to study, and I enjoy studying it in college as well. So the tests are what you guys have learned today. We are going to be doing a Kahoot. Let's see here. 1 second. So we're going to do a Kahoot. Let me just pull this up. So give me 1 second there. Let's see. All right, so just to reiterate for anybody who hasn't been to one of these lessons before, to join this Kahoot, you just go to www.kahoot.it, and then, or with the Kahoot app, and then you just enter in this game pin, and then you can put in your name. So we will wait a couple minutes for everyone. We don't, you shouldn't use your real name. Actually, it doesn't really matter too much though, because I know you guys are all good sports. You guys can just do like fun nicknames if you want to. Corn dog, I see. Beep. While we're waiting for people to join this Kahoot, that would be a good time to ask any questions or anything that like you guys had any difficulty understanding, or really anything. You guys can text us, and then I'll answer them while we're waiting for people to join the Kahoot. So we'll just wait for maybe 2 more minutes. If anybody's having any difficulty, signing in or logging in, please text us too. So we'll wait maybe 1 more minute and then we will start. Oh, we lost one. Oh, we lost another one. Okay. All right, 30 more seconds, and you can text us too if you need more time to join the Kahoot. We'll wait. It seems like we're waiting for a few more people, so we'll wait a little bit longer. If anybody wants more time or needs more time, could you also text me or my brother? If not, we will start in like 30 seconds.
John, just wait 1 second. I'm helping so.
Okay.
Okay, you can just get started, Sean.
All right, so we're gonna start now. All right. Are you ready? All right, nice. So if you remember, an electron is negative, and you also could say it has a charge of -1. So some of these, there might be more than one right answer, and you just can just choose one of them. Remember, let's see, let's go to the next one. Wow, so good. Okay. What is the charge of a proton? All right, nice. Everyone got that right. Good job. All right, so now this is trying to apply a little bit of the knowledge that we learned before. If it has 3 protons, 3 neutrons, and 2 electrons, what is its overall charge? All right, so to go over that, 3 protons, and remember protons we just said before is +1, right? Neutrons is +0 because it's neutral, and electrons are -1. So if we have +3 -2, what's that going to be? That's going to be 1. So that's why the overall charge is going to be 1. Nice. Atoms that are the same element have what in common? This is also what the number on the periodic table next to the element represents too. That's what it stands for. Yep, it's the same number of protons. Atoms that are the same element have the same number of protons, and in the periodic table, next to the element's name in the corner is the number of protons that the element has. All right, let's continue. So when do reactions happen? Do reactions happen randomly, when the atoms get really hot, when the reaction makes the atoms more stable, or when they bump into each other? So reactions happen. So this is I guess is a little bit of a trick question because atoms really do have to be next to each other, or sometimes they do bump into each other, and that causes them to react. But that's not the only thing, because for example, if we have two very stable atoms and they bump into each other, then they don't really want to bond because maybe bonding would put them at a higher energy or maybe make them unstable. So not all the time when they bump into each other will they react. But like we were talking about earlier, chemistry is the idea of stability, right? So when your reaction can make an atom more stable, put it in that comfortable position, it will want to do that. Let's do the next one. What is conserved in a reaction? So here we have mass and energy. Molecules might be a little bit tricky and it might be a little bit deceiving because molecules are not conserved, because like we showed before, we had atoms changing from one type of molecule to a different type of molecule. So the molecules themselves aren't conserved. They don't always end up as the same thing. Otherwise, the reaction wouldn't have anything different. What is conserved is mass and energy. So which of the following are types of energy? Oh, sorry that some people don't have enough time to choose. Next time we will make longer times for the questions. But like you guys all got it right. All these are different types of energy. You have, gravitational potential energy, sound, light, and heat. And remember, these different energies, they can become each other. Like when you explode something, or when you have like a fire, not only do you have the chemical energy turning into heat, but you have some of it turning into light and some of it turning into sound. Yeah. Next one. True or false? The more unstable a molecule is, the more likely it is to react. And yeah, Chad, gravitational is a type of energy. It's like potential energy. But that's a little bit more complicated, so we won't go too much into that today. Yes. Okay, so this was kind of split half and half, where some people chose true, some people chose false. So remember, if we have a reaction, going back to like our hill example, rolling down or up the hill would be considered the reaction. So was it more likely for the ball at the top of the hill to react or the ball at the bottom of the hill to react? And the answer is the ball at the top of the hill, because it's not satisfied, it's not comfortable in its position, so it wants to move, so it wants to react. When an atom is very stable, it doesn't really want to move, so it doesn't really want to react. So that's how you guys can think of that kind of concept, that idea. Let's see, was that our last question? No, we have 2 more questions. So true or false, this is the reaction for creating water. So I want you guys to think of our law of conservation here when you guys are answering this. Remember what we talked about before about like what needs to be conserved here? Yeah, so the answer is false, but the reason why it's false is it's true, we do have hydrogen and oxygen becoming something that has hydrogen and oxygen. But if you look on the left-hand side, there's only 1 hydrogen, and on the right-hand side, you have 2 hydrogens. So this would be a violation. This would break our rule for law of conservation of mass, because where did this extra hydrogen suddenly come out from? So that is why that this reaction is false. All right, so I see some changes in the leaderboard. So this is our last question. If atoms are like our solar system, what are electrons? Are they like the sun? Are they like the planets? Are they like Earth? Or are they like the asteroid belt? Yeah, they're like the planets. The sun would be something like the nucleus, the center of everything, right? The center and the biggest thing would be the protons and the neutrons, because like we talked about before, they have the most mass, they have the most matter, they have the most stuff inside of it. So again, that's like some way you could think of, atoms. Now, the way atoms actually look are a little bit different than what we said today and what we showed, but for the idea of like just getting started to think about atoms, this is like a way you guys can think about it, just like the solar system. All right, this is our podium. Congratulations, 3rd place, Cats Forever. 2nd place, myself, Yeet Myself. And then number 1, 8 out of 10. Wow, you guys all got 8 out of 10. That's a very good job. And then congrats to our runners-up, Hoot and Justin. But understand that you guys all did very well, and you guys learned definitely some complicated stuff today. What was it? This is like chemistry. It's something that you think about when you think about like high school classes and that sort of thing. So, good job. I hope you guys understood today's lesson. If you guys have any questions, feel free to stay and ask. If not, then I hope you guys have a good week, and my brother will probably say something at the end.
Oh yeah, thank you all for coming out, and thank you, Sean, for being our guest lecturer today. Yeah, we just hope that you guys had fun, learned something interesting, and hopefully, you think science is a little cooler now. So you guys can all leave the meeting now, and thank you for coming again.